My name is Alex and I'm going to be presenting our work at Techu in privacy-preserving crowd-GPS systems for us. But what are crowd-GPS systems? Crowd-GPS systems are a subset of crowd-sensing technologies that utilize the power of the crowd to solve interesting problems. The crowd in itself can be viewed as a distributed system, a system which is comprised by users that install an application in their smartphone. Upon installation of this application, each user becomes a member of a given crowd and helps solve interesting problems. Specifically in this work, we study and evaluate the crowd-GPS systems, which are systems that target the problem of tracking items in real life and solving problems such as discovering lost items. Imagine the scenario where somebody loses his bike and uses members of the crowd to locate it. But how does it work? In order to facilitate the tracking process, a common use case is the purchase of a special device, called a tag or a beacon, from a vendor. Vendors commonly provide also an application for free that the users might install in their phone, have to install in their phone, and thus they form a crowd for that given vendor. And that facilitates the tracking and finding process. Users that then lose their devices can query the central service and find the location of their lost property once a member of the crowd is in its proximity. This process is facilitated mainly using the Bluetooth Low Energy protocol. And the main feature that enables it is what is called an advertisement packet. Advertisement packets are special messages that are being broadcasted by tags and beacons every few milliseconds, ranging from milliseconds to a few seconds. The client app running on the user's phone, once discovering this and sensing this broadcast message, updates, senses the location that this beacon is sent, and uploads it to the vendor-controlled central service. And that enables, the assumption here is that the rightful owner of the property is the only one who can query and discover his lost item. Now that we know what crowd-GPS systems are, why is it an interesting problem for the community to deal with, and is it important? Even though these services have been with us for only a few years, we see that just the top vendors claim crowds of more than 10 million users, with projected sales looking at hundreds of thousands of tags sold per year. More importantly, because other vendors from other markets see how useful it is for users to be able to track and find their items, they are quick to jump in the crowd-GPS train. And vendors such as Samsung, for instance, promise to launch new product lines, like suitcases that will have embedded beacons in them. And we can see other vendors also seeing the valuable service and partnering up with vendors that provide this service. Now that we see that all this information is aggregated in a central system, and the next natural case that comes to mind is that being reporting our location somewhere central continuously is something very serious. As previous research has shown, location data are very sensitive. They can reveal very sensitive information, even by trivially looking at someone's history. In a very trivial way, somebody can find out where your home is or your work by just looking at the most visited location. More importantly, also, they can elicit other information, such as your sexual orientation or religious beliefs. So, given the sensitive nature of this data, is it a good idea to store them centrally? Do you trust the services? Can they ever be compromised? If you think that these concerns lie in the sphere of imagination, we argue that they are not. Ranging from actual applications now in the market that capitalize on tracking beacons, and the business model is making revenue out of your sensitive data. Even benevolent services may be compromised, and to see if there is any merit in our insight, we audited one of the two top crowd-GPS providers, Tracker. Unfortunately, we discovered an unprotected API call enabling anyone to be able to inquire about any device belonging to that vendor. Even worse, this attack, this vulnerability, leaves no traces. And the rightful owner has no way of knowing or being notified that there is a third party actually actively prying on his daily routine. But how did we discover it? Simply by downloading the app, decompiling it, we were able to retrieve approximately 95% of the code. And we examined all API calls. Through close observations, we discovered the API code that you see highlighted in blue. And someone may only require to just create a post for this call, appended by a special tracker ID number corresponding to his device. The sort of obfuscation for the tracker ID was the MAC address of the observed ID reversed in the network from a host owner. Upon issuing that call, unthrottled, somebody will continuously monitor you and retrieve information as shown in the JSON message that shows the last time seen and location data. Upon discovery of this exploit, we immediately disclosed it to the vendors. Unfortunately, even if, as you see, it's a trivial thing to fix, it took more than 9 months to complete. And along the way, they even updated their provided information and revealed more information, such as the name the user places to the tag. Given our discussion at this point, it seems that this very user-friendly service requires location data to be centrally stored. Otherwise, how would it facilitate the finding of lost items? Given the sensitive nature of this data, we placed as a cornerstone of our design and our study to find a system that provides the same functionality, but without centrally storing location data. We furthermore make no assumptions on whether the central service is trusted or malicious, and we place and evaluate our whole design based on this. Since our system is highly modular and offers different levels of guarantees for different challenges, I will only be able to present a few versions. Since our Techu is a crowd-sourced system, therefore the same entities appear in our system as well. We have the beacons, the crowd, the central service, and the user owner of the beacon. What is different, however, in our approach is that the broadcast tag identifier that facilitates the tracking of beacons is not constant. It's being created dynamically, periodically by the owner of the device and has some special properties that I will show in the next slide. Also, we follow a distributed approach. Since we do not store the location data centrally, we task the observers of each device to locally store some additional information, like each observation of a device. They hold the location data, and they never post it to the central service. True to our design that the central service is untrusted, the only functionality we demand out of our central service is to hold messages of the style observations, the reports from the observers that mean in the context, I have seen this device, contact me for more information. What are the special properties of the beacons? The user, the owner of every tag, periodically creates a set of keys, public and the private key, a secret key. He keeps a secret key because he will use it later on to prove ownership of the device, and updates its tag to broadcast the public key. The public server serves just as a bulletin board, as previously described, holding just observation or sightings of the device and never the location data. Bringing it all in a single view, you can see that even though the entities are the same in our system as in other crowd systems, we can see the distributed version. For instance, the location data are stored locally in the observers, not in the central service. The owners need only to keep track of their tags and the pair of secret public key. And the tags themselves broadcast this public key continuously. Once an observer takes a hold of that identifier, it uses it to create a report of this sort. It uses the public broadcasting key to encrypt its observer ID and places a hash of that key to the server. That allows the user to query the service for hashes corresponding to his tag ID and retrieve the potential matches. But as you can see here, this introduces since the server is public and everyone can take a hold of this information. Somebody can infer that, as you can see with the green color in the sum function, that this corresponds to a single tag. To ameliorate this problem, our system introduces salts. It takes the tag ID, adds a salt, and then posts it to that hash. And in order for the user to retrieve his keys, he now has to retrieve a packet of, if I may say, a packet of observations where his actual matches lie. And he has to search and decrypt through all of them to find his corresponding matches. And this is how the actual find where's my item query works in our system. The observer, the owner, once he wants to locate his item, retrieves a list of matches from the central service, decrypts them, and then directly contacts the observer. And in order for him to finalize the last step and retrieve the location data, he uses his secret key for a proof of ownership challenge. But that introduces a new implication inherent to our system. Once you contact an observer and ask him for the location of your item, he immediately knows that there is something wrong, you probably lost your item. To defend against this issue, our system follows the same strategy of decoy queries. Decoy queries occur when an owner that updates the tags he already has in his possession and thus has not lost, throws a random coin and decides based on that to issue a lost item inquiry about the device in his possession that he just updated. And that sets a set of inquiries in the cloud. And that makes malicious users unable to differentiate between actually lost items and really lost items. There is a performance rating here according to how many fake queries you implement. A few words about our implementation detail. We create an Android app that is able to update and read tags and following our protocol, and able to perform our security private protocol of location discovery. We use the Google Cloud messaging to evaluate it, and we chose a native cryptography for our public and secret key. Since we introduced new features in our system, we evaluated its impact to both the users and the server. Updating the tag for every 5 minutes introduces a 2% battery impact, which offers a good security and performance guarantee. The latency in the last step, where the users need to contact the observers and get their actual location, is 2 seconds in the worst case. To be able to get a hold of how much storage we require from the server, we performed the following experiment. For 41 days in our home city, which is an urban environment, we study how many observations of vehicles we have per hour, and we perform a crash test of collecting observations from Times Square during rush hour to get an upper bound of observations. The server storage for the first urban case scenario is about 25 terabytes for 1 week's worth of data, and for the Times Square upper bound experiment, we calculate 100 terabytes. Even though the number might seem too much, we argue that for a service serving millions of users, it's manageable. On the observer, the requirements are modest, requiring only 1.7 megabytes of data for the 1 week's worth of storage. Our system addresses the security and privacy implications and offers an alternative approach. However, it's not without its limitations. Being a cloud GPS system means that its inherent vulnerabilities such as central availability and malicious users can affect it. Moreover, something specific to our system, because we need to contact the observer and retrieve the location, it might take more steps in order to retrieve it. If one of the observers is offline, we might need to contact more of them, and that's why we get a list of observers. In conclusions, we designed and implemented Techu, a system that offers a secure and private alternative to currently commercial use of GPS systems. besides the incentives that it gives to the users in designing security, we believe that it also offers strong economic incentives to vendors because they don't have to deal with providing a secure service, and they maybe can share the same storage among different applications. In order to conclude, it is the author's view that the security and privacy should not be considered an add-on or luxury issue. It can affect us greatly, and we believe that it should be implemented in all services. And with that, thank you for your time.